Here is the notes. We did till here yesterday, isn't it?
Yes, sir.
The weak nuclear force is
Maybe, sir.
responsible for radioactive decay by being able to convert a proton into a neutron or vice versa. So yesterday I showed you the equation how to make neutron, how to make proton and electron from neutron, right? And here we got another one, that is proton can be also converted to neutron. In radioactive emission, also it is happening that proton is converting to one neutron and one positron. Are you familiar with this name, that positron? Hello, Ziba,
Yes,
Ziba,
sir.
are you familiar with this name, positron?
No, sir.
Okay, it is opposite of electron. Okay, there is another particle in the nucleus we get, that is called positron. I am showing you the equation. Yesterday I showed you how to get proton and electron from neutron. Today I will show you how to get neutron and positron from proton. Here is the equation. You see, a proton converts to neutron, one neutron. So proton has positive charge, right? Proton has
Yes, sir.
positive charge, and if you are getting neutron, that is not giving you any charge, it's neutral. So you have to balance the charge both the sides. That's why there is one positron. The symbol is like electron, but here we are getting one plus sign. That means its charge is equal to the proton charge. Or it is also equal to the electron charge, but opposite. So when this happens, yesterday we told that from neutron to proton and electron we get when number of neutrons are more, like C6. Yeah, Aisha is coming. C614, right? In this nucleus, how many neutrons are there?
6,
8.
8 neutrons. Here we
8.
get, yeah, you see this 6 is showing you the atomic number. Atomic number means proton number. Okay, so number of proton is here 6, right? In this nucleus. And number of neutron, how many? Because 14 is showing you the sum of neutron number plus proton number. So if you subtract 6 from 14, then it's coming 8. That is your neutron number. Yeah, Moshi, do you understand?
Yes, sir.
That's why this nucleus is radioactive, because number of protons and neutrons are not equal. We are getting here weak nuclear force, which is making this nucleus unstable, and that time we are getting the nucleus is balancing the number of protons and neutrons. How? Yesterday I showed you that neutron will convert to, one neutron will convert to what? Can anyone tell me?
Plus
Can
proton
One
minus electron.
electron and one proton.
excellent. So here we are getting positive and then we are getting electron negative, right? That's making both the sides charge balance, right? This side we are getting the charge is 0. So here we are getting plus and minus, then it's also becoming the balancing the charge is becoming 0. So here we got neutron converts to proton and electron. Why? Because number of neutrons are more in this nucleus. In some nucleus, there is happening that number of protons are more, number of neutrons are less. That time this one happens. Okay, if number of neutrons are less, proton are more. Everyone got it?
Yes.
Yes, sir.
Is it clear to everyone?
Yes,
Yes.
sir.
Yes, thank you so much. And if you want to see more, visual explanation, then you can go through these links. I gave you here some links, YouTube links. If you can manage some time, you can go through these links. That will give you some
Sir,
more
when will you
explanation.
give this?
Listen, Yakin, the
Yes, sir.
one I already gave, that one you go
Yes,
through
sir.
first.
Okay, sir.
When this topic will be over, then we'll upload these notes. Clear? But
Oh, okay,
video
sir.
video
Yes,
will
sir.
be available. Video will be uploaded time to time, but notes will be given at the end. Okay.
Oh, okay, sir.
Now we are done with the thing here. We got the weak nuclear force is responsible for radioactive decay by being able to convert a proton into a neutron or vice versa. Now we are going to another learning outcome, that is random emission of radioactivity in direction and time. We are saying radioactivity is random. In radioactivity, we are getting alpha, beta particles, and gamma radiation. The emission of these all particles and rays are random. What does random mean?
Like they don't come in fixed waves or fixed.
Yeah, they already gave us some clues
They
here.
are
Random,
scattered around.
yeah, random in direction and random in time. That means maybe in some cases we will get uh, five. I'm giving you one example, like five alpha particles. For example, five alpha particles in 1 second. Then again, we are getting 10 alpha particles in 1 second. This is happening. Okay, so it is random in time. The direction means it can happen in any direction, like it can go to right side or left side or any side it can go, the radiation. Okay, so it is random in direction and random in time. Now for more description, we will go to the writings here. Now, Yakin, you read this part, please. Hmm.
Detection of all the nuclei of a radioactive substance have the same probability of undergoing radioactive decay by emitting alpha and or beta particles and or gamma radiations. It is not possible to tell which nuclei will be the next in line to decay or how long it will take to decay, since it is independent of external conditions and the breakdown within the nucleus is completely random. In occurrence of radioactive emissions is random over space and time.
So I think it's clear to you from this description. However, I am elaborating a little bit. That is, uh, here this said it is not possible to tell which nuclei will be the next in line to decay or how long it will take to decay. So in one sample, we are calling, like we are taking one uranium sample, right, of 5 grams or 10 grams. Then in this 5 grams or 10 grams, there are lots of uranium atoms available, right? So out of those all hundreds of thousands of uranium atom, which one will first decay? We cannot say. Maybe which are available at the surface of the sample that can decay, or from the middle of the surface that can decay. Okay, that's why it can go to any side, right side, left side, upwards, downwards, anywhere the emission can come. In that respect, it is random in direction, and it is not also fixed that how long it will take. Already I explained it. That's why they are called random. The radioactive emission is, or radioactivity is random. Clear to you, everyone? And another point here, they are saying it's not depending on external conditions. Like if you are changing the pressure, or if you change the temperature, then it happens in chemical reactions. It happens that um, sometimes we are not having the reaction properly if the temperature is low, right? Isn't it? Hello.
Yes, sir.
Yes,
and
sir.
and also if the pressure is changing, that time also is affected the chemical reaction. But nuclear reaction, it does not depend on any pressure or temperature or any external condition. Like you are applying force, uh, at that time also is not affected. Okay, or you are not applying force, is not affected in that case. So it's independent of external conditions. Can we go to next part now? Hello.
Yes, sir.
Yes, sir.
Just you
Detection
have
of
to,
radioactive
yeah,
emissions.
yeah, just you have to remember this thing, that radioactive emission is uh, independent of external conditions, and it is random in direction and time. That's it. The other explanation, normally it does not come in exams. Okay, but I gave you the explanation. Okay, students, we are going to
Okay, sir.
the next one here, detection of radioactive emissions. Uh, in the radioactive emissions, we are getting alpha, beta, gamma. We cannot see them. We cannot smell them. We cannot touch them even. By any feelings, we cannot understand that there is radioactive emission. Okay, so how if someone is very close to any radioactive particles, or nuclear power station, that time there there is bad effect on their health. If they don't understand how much radioactive emission is coming to their body, then they cannot take measures to protect them from the radioactive emissions. So uh, we need some detectors to identify them, right? That's why we are using these detectors, Geiger Muller tube. We are reading it. Aisha, could you please read it? Aisha, hello. Aisha is there?
Yep.
Yeah, thank you. Please,
Okay.
here, please read it. Detection of radioactive emissions. This part you read.
Detection of radioactive emissions. Radioactivity is invisible, has no smell, makes no sound. In fact, it cannot be detected by any of our senses. However, because radioactivity affects the atoms that passes, you can easily monitor it using a variety of methods using following detectors: the Geiger Muller tube, Muller
Yes,
Geiger
continue.
Muller tube, photographic film, gold leaf electroscope, spark counter, cloud chamber, bubble chamber, and modern detectors.
Yeah, thank you so much. So we are having these detectors. Even I used Geiger Muller tube in our physics lab when I was a student of physics Dhaka University. That time we did some experiments on nuclear physics. I saw it, Geiger Muller tube, and we worked on it. When we were in master's students, that time we did some experiments of nuclear physics. And here we have the diagram of Geiger Muller tube. Uh, this one, you see the diagram. Here we are getting the reading. This one is the radioactive source. Hmm. And this one is the GMT. In short, Geiger Muller tube is called GM tube. Yeah. And here we have some description. Ziva, please read this part.
Most people have heard of a Geiger counter for measuring radioactivity. This is actually a Geiger Muller tube with some form of counter attached, which usually tells us the number of particles detected per minute counts per minute. GM tubes work using the ionizing effect of radioactivity. This means that they are best at detecting the alpha particles because alpha particles ionize strongly. Different models of GM tubes are available for detecting alpha, beta, and gamma emissions.
Yeah, so how does it work? A little bit given there. That is alpha particles, they have charges, right? They have two protons, so they have two positive charges. And these positive charges, when alpha particles pass through air particles, uh, or any kinds of gases, that time they can attract some electrons from the outer surface of those gas particles atoms. Okay, when they are picking the electrons, these electrons, the inside the GM tube, you see there is a black line here, right? Can you see this one?
Yes, sir.
So this black line is given high voltage, like 240, 400, 600, like that. So uh, positive voltage is given there. And when the electrons are coming out from other gas particles, that time this positive voltage are attracting them. Okay, when they are attracting them, that time uh, according this signal is going to the there is current flow, right? If electrons are there, there is current flow, isn't it? Hello.
Yes, sir.
So
Yes, sir.
when there will be lots of electrons coming, hundreds of thousands of electrons are coming here, that time it is called avalanche, like plenty of electrons. If the detector is getting that kinds of amount of electrons, then it gives a reading over here, right? And from there we can understand, yes, this source has this much radioactive emissions. Okay, is it clear to you? Hello.
Yes,
Yes,
sir.
sir.
Yes. So they said different
Sir,
methods. Yeah,
what
tell
is
me.
the uh, unit for counting the
Yeah,
radiation?
yeah, that is counts per minute. This is the unit.
No, sir, there was another unit
Yeah, becquerel.
they used
That
to
is
call.
becquerel. That is becquerel. According to the name of Henry Becquerel, there is one unit for radioactivity, radioactive emissions, that is called becquerel, and in short, it is BQ. This way,
Oh,
becquerel. Can you hear me? Becquerel. It is becquerel.
yes, sir, I can hear you.
Yes,
Yeah, yeah. This way, becquerel. BQ. According to the scientist name, it is when we are writing in short form. It is this way, BQ. Okay. His name is Henry Becquerel. Okay. Now we are going to more explanation, right, of GM2. Let's go there. Yeah. Ziba was reading, right? You continue this part. Ziba, you continue this part.
The tube is filled with argon gas and around plus 400 volts is applied to the thin wire in the middle. When a particle enters the tube, it pulls an electron from an argon atom. The electron is attached to the central wire, and as it rushes towards the wire, the electron will knock other electrons from argon atoms, causing an avalanche. Thus, one single incoming particle will cause many electrons to arrive at the wire, creating a pulse which can be amplified and counted. This gives us a very sensitive detector.
So you understood, right? What I explained, that's written here, and avalanche means plenty of electrons. Okay, when there are lots of electrons all together, this process is called avalanche. So this part is clear to you? Is it clear, everyone?
yes,
Yes, sir.
sir.
And another thing I am adding here, we are using here argon gas. Argon gas is a neutral gas, right? And it's monoatomic, isn't it? Hello?
Yes, sir.
Yes, sir.
We are when we are getting the GM tube, the GM tube is free from normal air. Only it is filled with argon gas. Okay, so that normally it becomes neutral because iron gas is a gas which is not reacting or making chemical reactions with surrounding any metals or anything. That's why it is called neutral gas. Do you know it? Hello, students.
Yes, sir, we know it, sir.
Do you know? Can you give me some other examples of neutral gas other than argon?
Xenon, radon,
Yes, yes, yes. These are also, neutral
helium,
gas. Why they are called neutral?
because they have 8 electrons in their last shell.
Only for that.
Same number of
They do
protons
not
and
accept or
electrons.
Yeah, they usually don't go for any chemical reactions with surrounding any gas or any metals or any objects, right? Normally they behave neutral. That's why they are called neutral gas. Okay.
yes, sir.
Then we are having another detector other than uh, what? Just now what we did? Which one we did
Geiger
just now?
GM
Yeah,
tube detector.
excellent, excellent. Okay, just I'm revising so that you can have in your mind. Now we are getting another one, photographic film. Photographic film. Can Moshi, your network is okay? If
Yes, sir.
it is fine, then you continue this part. Photographic film.
Sorry.
Yeah.
Okay, sir. From in 1896. Hello, sir.
Yes, yes, I'm getting you. Please
Okay,
continue.
okay, sir. In 1896, Henry Becquerel, working in Paris, discovered that uranium compounds would darken a photographic plate, even if the plate were wrapped up so that no light could get in. Radioactivity will darken fog, photographic film, and we can use this effect to measure how much radiation has struck the film. Workers in the nuclear industry were film but bad what? Like second, blur হয়ে গেছে।
Hmm. Maybe network problem.
হ্যাঁ
Yeah,
স্যার
continue.
which are sent to a laboratory to be developed just like your photographs. This allows us to measure the dose that each worker has received, usually each month.
Okay, continue.
Okay, sir. Figure 26.2. আচ্ছা ওইটা বাদ দিই। The bed bed key bed chase কি এটা?
Yeah, continue this. The badges have
Okay.
Badges.
windows.
It's have windows made of different materials so that we can see how much of the radiation was alpha particle or beta particle or gamma rays.
Okay, thank you so much. Now look here. Here is the film badge dose meter, and this one, the what can we say? The cross sectional or bisection is shown here, right? Sideways. You see here, we have here lead, right? Can you see here? Lead, then aluminum. Okay, students, are you getting this?
Yes, sir.
So look, we are having different windows in the badges. This one I am showing you. These are lead, aluminum, this. Okay, so these windows are helping us to understand how many alpha particles are there, how many beta particles are there, how many gamma rays are there. Later on, when we will discuss the properties of alpha, beta, and gamma, then we'll understand how can, by using aluminum lead, we can understand or we can detect alpha particles, beta particles, gamma particles. And another thing is here that photographic film is over there here. So this photographic film, we have some chemicals, and those chemicals are darken, will become dark or is foggy or is fade. Then from that one we can understand how much detection is there. Okay, if the uh, film is more dark, it's becoming more dark, then we understand that there is more radioactive emission available over there in the surrounding area. So they are taking this for a month. The dose meter, the film badge dose meter is replaced after 1 month. Okay, for 1 month they are checking the reading, and then changing the or replacing with a new one. So this one, is it clear to you? Photographic film. Hello.
Yes, sir.
Yes, sir.
Yeah. So now we are going for more discussions. The next one, that is the cloud chamber. The cloud chamber we are going to discuss. Here is the cloud chamber, and here. Okay, Aisha. Aisha, you please continue this one, the cloud chamber one.
Okay. The
Yeah,
cloud chamber.
yeah, loudly, please, a little bit loudly, huh? So
Okay.
that
The
recording is
cloud
good.
chamber. The cloud chamber. There are two types of cloud chamber, the expansion type and the diffusion type. In both types, alpha-beta particles leave trails in the vapor in the chamber, rather like high-altitude aircraft leave trails in the sky. The chamber contains a supersaturated vapor, e.g., methylated spirits, which condenses into droplets when disturbed and ionized by the passage of a particle. Alpha particles are best for this. You can clearly see the direction and energy of the particles. Occasionally, a
Continue.
particle collides with an air molecule and changes direction. A cloud chamber shows the randomness of radioactive emissions clearly.
Yeah, continue.
Okay.
Here.
Expansion cloud chambers use a vacuum pump to briefly produce the right conditions for trails to form, whilst the diffusion type shown in the video link given below uses solid carbon dioxide to cool the bottom of the chamber and produce a temperature gradient in which trails can be seen continuously.
Yeah, thank you so much. So here we got diffusion cloud chamber and expansion cloud chamber. In expansion cloud chamber, we are using one thing, that is methylated spirits and vapor, vapor of it. And when the alpha particles, beta particles are going there, then we are getting these kinds of, trace over there. And you see, some of the tracings are smaller, some are, longer, and some are also making any curve. So this way we can understand one thing, that is the radioactive emission is random, random in direction, random in size. uh, some of the emission is, you see, giving you long uh, tail, and that one is giving you more emissions. Okay. And some are giving you less, that are having less emissions. And finally we have here another one, that is the cloud chambers. Cloud chambers use a vacuum pump. uh, so it is also giving you the similar tracing. We are having the similar tracing. We can see that one in the video link. The video link is given there. So what is coming in our exams, that's not assessing you so many information available here. Only only we have to remember what, that one of the detectors name is the cloud chamber. And in cloud chamber we are identifying randomness of radioactive emissions clearly. That's it. Okay. Is it clear to you? For your
Yeah.
understanding, or for making you more confident with this instrument, or having more knowledge of this instrument, I just gave you some information here, so that you are getting at least little bit idea what is cloud chamber and how does it work. So can we go to next one,
Yes, sir.
or we
Sir, I
can
think time is up.
yeah, it's almost time is up, so we are having the review. That's better, right? We are having the
Yes, sir.
review. That will be better. So today what we learned, we are trying to get it from you first. Okay, then if there is anything missing, then I will add. First, Jiva. So today's class, what we learned from the beginning? Yeah.
Positron, how to get protons from there. Then radioactivity happens due to random happens in random motion and is independent of external conditions. Then the GM tube, cloud chamber, and the photo something.
Yeah, thank you so much. So today we got uh, the extension of last class. That is, we got here um, weak force. How does it work, and how from proton we are getting neutron and positron, right? Uh, then I added here one thing, that when we are having from proton to neutron and positron, if the number of protons are more, right, in the nucleus, isn't it? proton, the beta emission or beta decay, it happens due to the difference in what? Hello?
A ratio of proton and neutron.
Yeah, neutrons and protons. So if the number of neutrons are more, then we are getting electrons. If the number of protons are more, then we are getting positrons. Is it clear?
Yes, sir.
Okay. So we finally we are getting the detectors, right? Why we are using the detectors?
To detect the amount of radiation.
Yeah, because by our feelings or sense we cannot detect radioactive emission. That's why you have to use some special instruments, right? We explained how many today? We mentioned how many today? How many detectors we discussed today? 3, right?
3.
Yeah.
3.
The first one is GM tube or GM counter. The second one is uh, uh, photographic plate or photographic badges. Then the third one is the cloud chamber. Okay. Thank you all for joining. Allah Hafiz. Stay safe.
Sir,
Stay safe. Okay.
sir,
Yes. Yes.
Is it possible to give those notes before the class so that I can print them out? Because my
Okay. I
head aches
today
whenever I look at this.
today I will give no problem. No problem.